Welcome back, dear students. In this video lecture, we are going to discuss about Introduction to Network Layer. In the previous lecture, we have discussed about Introduction to Data Link Layer. So this is taken from chapter 18 from your Horizon textbook. In this chapter, we are going to learn about what are IP addresses, what are different versions in IP addresses, and only one topic is there for your syllabus, that is IPv4 addresses. One more version of IP addresses are there, IPv6, that we are not going to study here, but I'll give you some information about IPv6 whenever it is needed in the video. So what are IP addresses first? IP addresses, they are known as identifiers. IP addresses are the identifier used in the IP layer. Okay, you have seen many types of addresses in TCP/IP protocol suite. So in physical layer, we had some point of identifiers there. In data link layer, we have some identifiers. There we have used link layer addresses, which we have discussed in the last video. In network layer, you are going to discuss about IP addresses. So these are the identifiers here. And in transport layer, we have discussed about port numbers. So that are the identifiers there in transport layer. So coming to IP layer or network layer, so the identifier will be IP addresses. Okay, so the identifier used in the IP layer of the TCP/IP protocol suite to identify connection of each device to the internet is called as internet address or IP address usually. Okay, so an IP address usually is of 32-bit. It is a 32-bit address. It uniquely and universally defines the connection of a host or a router to the internet. Then the IP address is the address of the connection, but not the host or the router. Okay, you should note this point, because if the device is moved to another network, the IP address is changed. Okay, so IPv4 addresses are unique in the sense that each address defines one and only one connection to the internet. So if a device has two connections to the internet, then it will be having two IP addresses like that. Okay, then IPv4 addresses are universal in the sense that addressing system must be accepted by any host that wants to be connected to the internet. So key points from this slide is we have IP addresses in IP layer. Then it is a 32-bit address. IPv4 version 4 address is 32-bit address. Usually we will deal with IPv6 addresses. It is 128-bit address. What is the meaning of these two? I'll tell you, and why we have evolved to IPv6, I'll tell you. Okay. And one more key point to be noted here is these IP addresses are unique. Okay. So next point, a protocol like IPv4 that defines addresses has an address space. Okay, we will discuss about address space. What is an address space actually? So an address space is the total number of addresses used by that protocol. So here we are discussing about IPv4 protocol. So when you consider address space of a IPv4 protocol, then we should tell, or it is the total number of addresses used by that protocol. So if a protocol uses B bits, suppose the protocol is using B bits to define an address. I have told in previous slide that IPv4 protocol is using 32 bits. So B here refers to 32. Okay, the address space is 2 raised to B. Keep this thing in mind. So the address space is 2 raised to B here. So B for IPv4 is 32. So the address space of IPv4 is 2 raised to 32, or it is some 4 billion devices it can be connected. Right. So using IPv4, we can only connect 4 billion devices. Keep this thing in mind. So as and when the number of devices became more than billion, so there was a point that this IPv4 address space may be exhausted in coming near future. So we migrated into IPv6. There in IPv6, the value of B is 128. So the address space is 2 raised to 128. That many number of connections can be made at any point of time using IPv6, or that many devices can be connected to internet, in other words. Okay, that is the address space of IPv6. Coming to IPv4, it is 2 raised to 32, not 232 that is given in slide here. It is given by mistake. It is 2 raised to 32. Okay, so or 4 billion devices. Right. This is notation, IPv4 notation. We have three notations here as discussed in the slide. There are three common notations. The first one is binary notation or base 2 notation it is called as. The second one is dotted decimal or it is base 256, and the hexadecimal notation base 16. See, I have told you for dotted decimal it is not base 10, it is base 256. Why it is base 256, I'll tell you. Coming to binary, you got to know that it is these addresses can be represented in zeros and ones, so it is base 2. Okay, this is clear. Then coming to dotted decimal, it is base 256, not base 10 because of decimal word there. So here the range of IP addresses starts from this number starts from 0 to 256. That is why it is base 256. Okay, then coming to hexadecimal, it is base 16 as you all know. So in binary notation, an IPv4 address is displayed as 32 bits. To make the address more readable, one or more spaces are usually inserted in between each octet. So we have inserted, after 8 bit we have inserted a space like that. So in binary, all the IP addresses written in zeros and ones. So for between each octet we leave a space. Okay, this is all about binary notation. Coming to dotted decimal notation, the IPv4, to make the IPv4 address more compact and easier to read, it is usually written in decimal. That is why this dotted decimal notation came into existence. Because each byte is only 8 bits, each number is dotted. Each number in the dotted decimal notation is between 0 to 255. So here you can say if all these numbers are 1 in this octet, then it will be 255, right? 256, right? So that is why we have for one octet, one dotted decimal notation will be there, right? This is conveyed by this is conveyed by this is conveyed by this, and like this. Okay, so this is written as 128, this is written as 11, this is written as 3, this is written as 31. So this is more usual notation that we use in our day-to-day life. So each hexadecimal digit is equivalent to 4 bits. Okay, keep that thing in mind. Each hexadecimal digit is written as 4 bits, right? Because each byte is only 8 bits, each number in the dotted decimal notation is between 0 and 255, and we have the last one hexadecimal 4 bits equivalent. Then this means that a 32-bit address has 8 hexadecimal digits as it is shown in the figure. Okay, each hexadecimal digit is equivalent to 4 bits, I already told you. Then this means that a 32-bit address is divided as 8 hexadecimal digits. Then this notation is often used in network programming, not in our day-to-day life, right? So this figure shows you the IP address in 3 notations that we have discussed. Okay, then coming to the next part, hierarchy in addressing. This is very important. In any communication network that involves delivery, such as a telephone network or a postal network, the addressing system is hierarchical, right? In a postal network, we will be having mailing addresses including the country, state, city, street, house number, and name of the mail recipient. Similarly, a telephone number is divided into country code, area code, location exchange, and the connection. Similarly, here in our example, a 32-bit IP address is also hierarchical. It is divided into 2 parts. The first part is called as prefix and the second part is called as suffix. So totally 32 bits will be there. Here in 32 bits, n bits will be divided or called as prefixed, and the remaining bits, that is 32 minus n bits, are mentioned as suffix bits. So you have 2 hierarchy in addressing, IPv4 addressing, that is prefix and suffix. Okay, so the second part is called as suffix. First part is called as prefix. Prefix defines the network, okay, and the suffix defines the node. So you should keep this thing in mind. This defines network and this part defines node. Okay, what is network and what is node is mentioned here. So this is network. To this network, how many nodes are connected? 3 nodes are connected. That is defined by suffix. This network is defined by prefix, in other words. Okay, please keep this thing in mind. Then a 32-bit IPv4 address is also hierarchical, as we have discussed. Okay, then a prefix can be a fixed length or variable length. The network identifier in the IPv4 was first designed as a fixed length prefix. So this scheme was now obsolete and is referred to as classful addressing. So the new scheme which is referred to as classless addressing, shortly we are going to study it. It uses a variable length network prefix. First we will discuss about classful and then we will discuss about classless. What are these? We will discuss. Okay, the explanation I already told you. So this classful addressing and classless addressing. So what are these? These are actually the schemes for IPv4 addressing. So classful addressing, this one is obsolete. So when the internet started, and an IPv4 address was designed with a fixed length prefix. So prefix, why prefix is used? To uniquely identify the network, we have studied, right? So in previous olden days, this prefix length was fixed. But to accommodate both small and large networks, 3 fixed length prefix were designed. So you can see here in this figure, there are 3 prefix lengths. Class A, a little bit, only 8 bits you can observe here. Class B, prefix length is 16 bits. Class C, prefix length is 24 bits. Okay, so prefix length, we can call it using n. N is 8 in case of class A, n is equal to 16 in case of class B, n is equal to 24 in case of class C. So as and when, you can observe here, as and when you decrease n, that is value of prefix, suffix will get increased. Okay, so what we have discussed about prefix and suffix, prefix describes networks, okay, and suffix describes nodes. So what analogy you can draw here? In class A, number of networks that can be connected is less. Okay. In class A, number of nodes that can be connected is more. Okay. Then coming to class B, number of networks and number of nodes are a little bit same. That is, you can connect 2 raised to 16 networks and you can connect 2 raised to 16 nodes in each of these networks. That is the meaning of it. Right. Then class C, you have prefix length of 24 bits. That is, you can hold up to 2 raised to 24 networks. 2 raised to 24 networks can be named in class C. Then what about suffix? Suffix tells about nodes. Then in each of these 2 raised to 24 networks, you can name 2 raised to 8 nodes. That is the meaning of it. Okay. Class D and class E are serving some purpose. I will discuss it later. Okay, so when the internet started, IPv4 addresses was designed for fixed length prefix. That is what we are learning. The whole address space was divided into 5 classes here. What are the classes? A, B, C, D and E. So whenever classful addressing is asked in exam, so you have to write about class A, class B, class C, class D and class E. You have to draw this diagram and you have to explain. Okay, although classful addressing belongs to past, it helps us to understand classless addressing. That is going to be discussed in next part of the video. Then in class A, network length is 8 bits, but since the first bit, which is 0, defines the class, we can have only 7 bits as a network identifier. This means that there are only 2 raised to 7, that is 128 networks in the world that can have a class A address. Okay, so 0 is the prefix here. So leaving that, how many numbers are there? What is the value of n? N is 7, that is 8 minus 1. So you can have 2 raised to 7, that is 128 networks. Only 128 networks in this world can have class A addresses. Then coming to class B, the network length is 16 bits, but since the first two bits, which are 1 0 here, have occupied already, we have how many bits remaining? 14 bits remaining. Then we can have 2 raised to 14, that is 16,384 networks in the world that can have class B address. Then all addresses that start with 110 belongs to class C. In class C, the network length is 24 bits, but since 3 bits define the class, we can have only 21 bits as the network identifier. This means there are 2 raised to 21, or it is 20,97,152 networks in the world that can have class C address. And class D is not divided into prefix and suffix. It is used for multicast addresses. Then in the last class, I have told you what are 3 types of addresses, that is unicast, multicast and broadcast addresses. So class D addresses are usually reserved for multiclass addresses. Then all the addresses that start with 1111 in binary belong to class E. As in class D, class E is not divided into prefix and suffix and are used as reserve purpose. Okay, so I'll give you a assignment here at this point of time. We have our college network. We have our own IP addresses given by our system admin. So it starts with 162 something like that. So write it in binary form, write it in dotted decimal form, write it in hexadecimal form, and please tell me in which class they belong to. Okay, after converting, if the IP address, after converting it to binary, if the IP address start with 0, then you can say that it belongs to class A. If it starts with 10, then you can say that it belongs to class B. If it starts with 110, you can say that it belongs to class C. If it starts with 1110, then you can say that it is class D, which is not possible, and class C is also not possible because they are reserved for future use or multicasting purpose. Okay, so this is all about classful addressing. Then coming to classless addressing. Wait a second. Coming to classless addressing. So subnetting and supernetting in classful addressing did not really solve the address depletion problem. So as you all can see that address depletion problem happens in case of class full addressing. Class full addressing means class A, class B, class C, class D, that addressing. And class less addressing means that we are going to study now. So what is address depletion then? That is discussed over here, right? So address depletion, so the reason that classful addressing has become obsolete is address depletion. Okay, since the addresses were not distributed properly, the internet faced with the problem of addresses being rapidly used up. So I told you only 128 networks can have class A. So how many organizations are there? There are millions of organizations in a country itself, or there are billions of organizations in the world. So how to cope up with this growing number? We cannot do it with class full addressing. So we went to classless addressing. So the disadvantage of class full addressing, that is address depletion and subnetting and supernetting, didn't meet what we expected, right? The growing needs of organizations. Then we went to classless addressing. So subnetting and supernetting in classful addressing did not really solve the address depletion problem. So with the growth of internet, it was clear that a larger address space was needed as a long-term solution. So the larger address space, however, requires that the length of IP addresses also be increased. Okay, so which means that format of IP packets need to be changed. So this gave rise to IPv6 as a long-range solution. A short-term solution was also devised for this. So that is classless addressing. Okay, there were another motivations for classless addressing. That is, during 1990s, internet service providers came into prominence. An ISP is an organization that provides internet access for individuals. We have discussed in this point in class. So ISP can provide these services. So ISP is granted a large range of addresses, and then ISP subdivides the addresses into groups. 1, 2, 4, 8, 16, and so on like that. So giving a range of IP addresses to a company like that. So in 1996, the Internet authorities announced a new architecture called as classless addressing. So what happens here in classless addressing, variable length blocks are used to that belong to no classes. So we use blocks here, whereas in classful addressing we have used prefix and suffix method. So in classless addressing, the whole address space is divided into variable length blocks. Keep this thing in mind. Variable length blocks. Here no fixed length will be there. Like in class A, n bits will be as prefix, remaining 32 minus n bits will be suffix, like that. Here it is not there. So the prefix is an address defines the block, and the suffix defines the devices or nodes. So theoretically we can have a block of 2 raised to 0 to 2 raised to 32 addresses. So one of the restrictions, as we discuss later, is that number of addresses in a block needs to be power of 2. That is one of the restrictions here, right? So you can see from figure, this is how variable length blocks in classless addressing looks. So unlike classful addressing, the prefix length in classless addressing is variable, always variable. So we can have a prefix length that ranges from 0 to 32. That is no suffix at all. Then size of the network is inversely proportional to the length of the prefix. Okay, a small prefix means a larger network, and a large prefix means a smaller network. Okay, do you understand that? A small prefix means larger network. Larger network has many nodes. So if the value of n becomes less, prefix becomes less, suffix becomes more. What is the meaning of that? Suffix means number of devices connected. So number of devices connected becomes more. If n becomes less, the network becomes large. If n becomes more, networks becomes, or the nodes in the network becomes less. That is the meaning of that. Okay, then we need to emphasize that the idea of classless addressing can be easily applied to classful addressing. So an address in a class A can be thought of as a classless address in which prefix length is 8. Then an address in class B can be thought of as classless address in which the prefix is 16, and so on for C, D, and E. So in other words, classful addressing is a special case of classless addressing. That's it. Then we will move to the next part, that is slash notation, CIDR it is called as. So that is CIDR, I'll abbreviate it, classless interdomain routing. Okay, so the first question that we need to answer in classless addressing is how to find the prefix length if an address is given. So I'll tell you that 12.24.76.8. So what is the prefix and what is the suffix? How you will get to know, right? How you will get to know what is the number of prefix and what is the number of suffix? Then that is what is the number of how many networks are there in this IP address and how many nodes are connected to this network. How you will get to know? So to solve that, since the prefix length is not inherent in the address, we need to separately give the length of the prefix. In this case, the prefix length n is added to the address separated by a slash. So here it is given slash n. Okay, so this is slash notation. So what this slash n refers to? N refers to number of bits in prefix, right? The notation is informally referred to as slash notation and formally as CIDR, that is classless interdomain routing. Okay, then or it is also pronounced as CIDR. An address in classless addressing can then be represented in as shown in this figure. So in other words, an address in classless addressing does not define the block or network to which the address belongs to. We need to give prefix length also. Okay, then in the next part we are going to extract information from an address. Okay, so given any address in the block, suppose in this example now, we normally look to know 3 pieces of information about the block to which the address belongs, the number of addresses, the first address in the block and the last address, right? So we look into 3 pieces of information. The first one is the number of addresses, the first address in the block and the last address in the block. Okay, so we will discuss about these three things. Then since the value of prefix length n is given, we can easily find these three pieces of information. Okay, so the number of addresses in the block is found as n is equal to 2 raised to 32 minus n. Okay, so number of addresses will be n is equal to 2 raised to 32 minus n. That is, given IP address and its slash notation in CIDR strategy or scheme. So what are the three information you can devise? First one is total number of addresses in that network. So what is total number of addresses in that network? To get to know that, you need to know this information, suffix information, right? So given n bits, the value of n bits will be given in slash notation. So take that information, you will get 32 minus n. So total number of devices will be 2 raised to 32 minus n. That will answer your first part. Okay, the second part is what is the first address and what is the last address. Okay, so the first address will be we keep the n leftmost bits and set the 32 minus n rightmost bits to zeros, all zeros. So let the suffix bits, all these bits, be 0, then it leads to the first address. Then if the suffix bits are all 1, then it leads to last address. Okay, so this is how we are going to discuss. Given an IP address, this is how we are going to find all the information, three information. So we'll solve a problem here. Read out this problem. A classless address is given as 167.199.170.82. You can say point or you can say dot. We usually say dot 167.199.170.82/27. What is this 27? It is n. Yes, it is n. So we can find the above three pieces of information as follows. The number of addresses in the network is 2 raised to 32 minus n. What is the value of n? It is 27. So n 2 raised to 32 minus n will be 2 raised to 5. That is 32 addresses. So 32 addresses are there in this network. The first address can be found by keeping the first 27 bits and changing the rest of the bits to zeros, like this. Okay, that this is first address. And coming to the last address, keep all the bits as it is up to 27, then change these last 5 bits to 1. If you change these last 5 bits to 1, then it is last address. If you change these last 5 bits to 0, then it is called as first address. Right, this is all about classless interdomain routing. We have one more problem. We repeat example 18.1 using the mask. The mask in dotted decimal notation is 256.256.256.224. The AND, OR and NOT operations can be applied to individual bytes using calculators and applets at the book website. So we are using mask here. I'll solve this. But before that, we need to know what is address mask. So another way to find the first and last addresses in the block is to use the address mask. Address mask is a 32-bit number, okay, in which the n leftmost bits are set to 1 and the rest of the 32 minus n are set to 0. Okay, so the prefix bits are set to 1 and the suffix bits are set to 0. A computer can easily find the address mask because it is complement of 2 raised to 32 minus n minus 1. So the reason for defining a mask in this way is that it can be used by a computer program to extract the information in a block using 3 bitwise operators, not, and, or not. So the number of addresses in the block n is not plus 1. Okay, the first address will be and the last address will be or. We will see this operation. So the number of here they have given IP address as 256, 256, 256. This is all 1. If you make all the leftmost bits as 1, then you will get 256, 256, 256. Then we have something called as we have something that is there as 224. So what is given? They need to, or we need to tell what is number of addresses and first address and last address. So n, that is not number of addresses, is given by n. We have to use not mask as per the explanation I have done. So for first address you have to use AND operation. For last address you should use OR operation. Okay, so what you have to do is you have to make all the values not here, then you will get that there are 32 addresses. Then you have to perform AND operation, then you will get this address. You have to perform OR operation with the given IP address, then you will get this notation, last address notation. This is how we represent using address mask. Okay, then one more problem we have. In classless addressing, an address space cannot define the block address belongs to. For example, the address 230.8.24.2 can belong to many blocks. Some of them are given below with the value of prefix associated with that block. So this is, if prefix length is 16, it will be 230. If prefix length is 20, again it is 230. Then if prefix length is 26, again it is 230. All the first addresses are same here. Then coming to the second addresses, they are also same up to some point. Okay, so this will happen. This is the problem that will happen if you use address masks. Okay, so we will discuss it further. We will discuss network address. The above example shows that given any address, we can find all the information about the block. The first address, the network address, is particularly important because it is used in routing a packet to its destination network. So you can see here in this figure, for the moment, let us assume that an internet is made up of m networks, network 1 to network m in this figure, and a router with m interfaces. So this router has m interfaces. It has one interface with network 1, it has one interface with network 2, and it also has interfaces like that with all the network till network m. So it has m interfaces. Okay, when a packet arrives at the router from any source host, the router needs to know to which network the packet should be sent, from which interface the packet should be sent out. Right, when the packet arrives at network, it reaches its destination host using another strategy that we will discuss in later part in computer network subject. So there are protocols for that. So here figure 18.22, it shows the idea. After the network address has been found, the router consults its forwarding table. It will be having something called as forwarding table. So this forwarding table assures the router to which network it has to forward. Okay, at this point of time, keep in mind that we have forwarding table to do this task. Right, so the network address is actually the identifier of the network. Each network is identified by its network address. Okay, then going to the next concept, we have a problem here, 18.4. that is, an ISP has requested a block of 1000 addresses. That is, an internet service provider has requested a block of 1000 addresses. Since 1000 is not a power of 2, 1024 addresses are granted. The prefix length is calculated as n is equal to 32 minus log 1024 to the base 2. So that is 22. So an available block is given. Its IP address is 18.14.12.0/22. What is 22? 22 is n. N refers to prefix. Prefix refers to number of networks in that IP address is granted to ISP. It can be seen that first address is in decimal is this number 302,910,464, which is divisible by 1024. So that is the analogy that all the addresses will be in the power of 2. Okay, going to the next part, problem 18.5. An organization is granted a block of block of addresses with the beginning address 14.24.74.0/24. The organization needs to have 3 subblocks of addresses to use in its 3 subnets. One subblock of 10 addresses, one subblock of 60 addresses, and one subblock of 120 addresses. Design the subblocks is the question that is asked. Okay, we shall see the solution. So there are how many addresses? 2 raised to 32 minus 24 addresses, or the value of capital N. Capital N will be 2 raised to 32 minus N. What is the value of small n? Small n is 24, as it is mentioned here. Okay, so the value of capital N will be 2 raised to 32 minus 24, that is 256. So there are 256 addresses in this block. So the first address is how to find first address and how to find last address we have already discussed. That is, we have to just make, here in this case, we have to just make the remaining bits. 24 bits means 8 bits will be for this, 8 bits will be for this, 8 bits will be for this. So 8 into 3 is 24. The last 8 bits will be your suffix. So make all the suffix bits as 0, that will be your first address, and if you make all the suffix bits as 1, that leads to 255, that will be your last address. Okay, so this is how we are going to find first and last addresses. To satisfy the third requirement, we assign addresses to subblocks, starting with the largest and ending with the smallest numbers. So A, the number of addresses in the largest subblock which requires 120 address is not a power of 2. So we allocate 128 addresses. So N1 can be found here, that is 32 minus log 128 to the base 2, that is 25. Right. So the first address will be, first address in this block will be 14.24.74.0/25. Okay. So 25 units are taken here, only 7 units are suffix units. So if you make all zeros, that will be starting address. If you make 7 bits, last 7 bits as 1, it leads to 127. So that is last IP address. Okay, then coming to B, the number of addresses in the second largest subblock which requires 60 address is not a power of 2, so we will take 64. Similarly, do all these tasks as we have done here, so you will get first and last address like this. Then coming to C, there are here it is 10 addresses, so it is not power of 2, so we will take 16 addresses. Then you will get subnet as 28, or slash notation, or n, the value of small n is 28. So the remaining 4 bits you make 1, that leads to 207. The last 4 bits you make 0, then it leads to 192. So this is how you should solve problems. Okay, so this is the notation here. After solving, we have marked the subblocks. This is not needed actually. If you skip this, it is okay. Whatever we have solved, the same thing is picturized here. Okay, then the next problem, figure 18.24, we will see it. This figure, I'll read out the question. Figure 18.24 shows how 4 small blocks of addresses are assigned to 4 organizations by an ISP. This is an ISP. So how 4 small blocks of addresses are assigned to 4 organizations by an ISP is shown here. So the ISP combines these 4 blocks into one single block and advertises the larger block to the rest of the world. So any packet destined for this larger block should be sent to this ISP. So it is the responsibility of the ISP to forward the packet to the appropriate organization. So this is similar to routing we find in a postal network. All the packages coming from inside a country are sent first to the capital and then distributed to the corresponding destinations. Right. So this is ISP. So this is internet. So whenever any messages came here to ISP, it searches to which network it has to send and then subdivided like this. It is similar to postal analogy, that how post offices serve their these things, couriers. Okay, the next concept is DHCP, that is Domain Host Configuration Protocol. So we have seen that a large organization or an ISP can receive a block of addresses directly from ICANN. ICANN is organization that provides network addresses. Okay, and I have told you in module 1 that ICANN also provides port numbers in transport layers. Okay, which port number to which protocol, like SMTP, HTTP. So these have port numbers. So these are assigned by ICANN already, right? Then and a small organization can receive a block of addresses from an ISP. So after a block of addresses are assigned to an organization, the network administration can manually assign addresses to individual hosts or routers. So however, address assignment is in an organization can be done automatically. Right, this automatical addressing is done using a protocol again. That protocol is named as Dynamic Host Configuration Protocol. So DHCP is an application layer program. It uses a client server paradigm, right? So you can see to the figure. This is DHCP message format. So DHCP message format, DHCP is a client server protocol in which client sends a request message and the server returns a response message. So before we discuss the operation of DHCP, let us see the general format of DHCP message. So most of the fields are explained in the figure. This part, all the fields are explained, but we need to discuss the option field, which plays a very important role in DHCP. So this 64 byte option field, see the option field, this field, this is 64 byte option field, has a dual purpose. It can carry either additional information or more specific vendor information. The server uses a number called a magic cookie in the format of an IP address with a value 99.130.83.99. When the client finishes reading the message, it looks for magic cookie. If present, the next 60 bytes are options. An option is composed of 3 fields. 1 byte tag field. Here you can see 1 byte tag field, then a 1 byte length field and a variable length value field. There are several tag fields that are mostly used by vendors. So if the tag field is 53, the value field defines one of the 8 message types. You can see here one of the 8 message type: DHCP discover, DHCP offer, DHCP request, DHCP decline, DHCP acknowledgement, not acknowledgement, release, and inform. That is the value that is given here, right? Value for the value field, we have 8 different options like that. So operation of DHCP, this is important in this chapter. Explain the operation of DHCP. So you have to draw this diagram and you have to explain. So I'll explain each and every step one after the other. We'll go back to that figure again. So we have client server. As I've already told you, DHCP is a client server protocol, okay, in which client sends a request and the server returns a response message. Please keep this thing in mind. So we will see what happens now, right? So client and server are interacting. What they interact, let us study. There are 4 interactions. The first interaction, what is my IP address? That is the question client asks to the server. Okay, so how it will ask? The server will say that at the end, it will say that your IP address is this and this. So how this is done? This we have to know. The first one, that is DHCP discover. So the joining host, this is the joining host. This is the joining host. It creates a DHCP discover message. Here in this case, client is the joining host. So it creates a DHCP discover message in which only the transaction ID field is set to a random number. See here, transaction ID field, it is set to 1001. Okay, no other field can be set because the host has no knowledge with which to do so. So the message is encapsulated in a UDP user datagram. UDP is connectionless service. Okay, so we will discuss it in transport layer, what is UDP and what is TCP and how they work. So it is not part of this subject. It is part of computer network subject which you are going to learn in next semester. Okay, then this message is encapsulated in a UDP user datagram. So with source port set to 68, source port is set to 68 and destination port is set to 67. We will discuss the reason for using these two well-known port numbers later. Right, the user datagram is encapsulated in a IP datagram with a source address set to 0000 or this host, and the destination address is set to 255.255.255.255, that is called as broadcast address. This we have learnt. Then the reason is that joining host knows neither its own address nor the server address, so it has set source address as 0, all zeros, and destination address as all ones. So this is first step. So in first step, DHCP discover message will be sent by client to the server. It doesn't know its own address and it doesn't know the address of the server, so it sends a random message with source port as 68 and destination port as 67. This you have to know. Then second one is this message is received by server. Now server, what it does, it responds with a DHCP offer message, in which the your address field defines the offered IP address, and for the joining host and the server address fields includes the IP address of the server. So the message also includes the lease time for which the host can keep the IP address. So I'll show you the next scenario, that is DHCP offer. You see, look at the options present here. Transaction ID is 1001, the same time. Then lease time is 3600. Till that point of time it can use this IP address. Then your address, it has given some address. It has given some address, that is 181.14.16.182. It is saying that client should observe this IP address, whereas server's IP address is 181.14.16.170 is server's IP address. So the source port is 67. Just vice versa of this, source port is 67, destination port is 68. So source address, so where it is coming from, it is coming from server, so it will put its own address, that is 181.141.16.170. and what is the destination address? It is sending as a broadcast address. Okay, this is in second step. Coming to the third step, what happens in third step? It is DHCP request. So the first step is discover, offer, request, and acknowledge. Right. So in the third step, the joining host receives one or more offers and selects the best of them. The joining host then sends a DHCP request message to the server that has given the best offer. The fields with known value are set. The message is encapsulated in a user datagram with port numbers as the first message. The user datagram is encapsulated in a IP datagram with the source address set to new client address, but the destination address is still kept as broadcast address. See here that you can see whatever it has sent, that is 182 at the end, so it accepts that and still it sends with the broadcast address. Right, this is DHCP request. Right, whenever source or client makes this decision then and send it to server, then the server send back the last message, response message, that is acknowledge. Whatever client has done the action, it acknowledges it. So finally the selected server responds with a DHCP ACK message to the client if the offered IP address is valid. If the server cannot keep its offer, the server sends a DHCP NACK, that is not acknowledged, message, and the client needs to repeat the process. So this message is also broadcast to let other servers know that request is accepted or rejected. That is why the destination address is again broadcast address. Okay. So this is FSM for DHCP client. Transition diagram. The transition states here are init, selecting, requesting, bound, renaming, and rebinding. So these are discussed with your DHCP discover, DHCP request, DHCP ACK, and DHCP release. So whenever they offer, this is something called as transition state. After this state, it is going to this state, it is going to this state. It is like flow chart. Okay. Then the last topic here is NAT, that is the network address resolution. It is called NAR or NAT, network address translation. Okay, so the distribution of addresses through ISPs has created a new problem here. Right, assume that an ISP has granted a small range of addresses to small businesses or household. If business grows, then what happens? Or the household needs a larger range. The ISP may not be able to grant the demand because addresses before and after the range may have already been allocated to other networks. So in this situation, only a portion of computers in a small computers need access to the internet simultaneously. So this means that number of allocated addresses does not have to match the number of computers in the network. So you can see this scenario. So here the private network uses private addresses. So this is private network. It uses private addresses. As I've already told you in class, there are two types of IP addresses, public IP address and private IP addresses. So here the private network, whatever I have marked, site using private addresses, it uses private addresses. The router that connects to the network to the global address uses one private address and one global address, that is public address. So this router, it uses one private address and one public IP address or global IP address. Okay, the private network is invisible to the rest of the internet. So the rest of the internet only sees NAT router through this IP address, that is 200.24.5.8. So this is what is network address translation. So whenever any of these computers send some information to the other part of the world, they convert their source address is converted into a global IP source address using NAT router. Okay, then it is sent to the outside world, and when some information is coming from outside world to the private network, again the vice versa will happen. It is converted to global IP address into private IP address. That is what is network address translation. So this is what is shown here. Source 172.18.3.1, this is sending some request. So whenever this packet goes through the NAT router, the source IP address changes to NAT router's IP address. Okay, following this, you can see it from the figure. Whenever from the outside internet some packet is coming, destination IP address is 224.5.8. this is it. Then it converts this NAT router converts it into respective IP address, private IP address. This is called as address translation process. So how this address translation is done, we have a separate part for that. We have a translation table. So the reader may have noticed that translating the source addresses for an outgoing packet is straightforward, but how does the NAT router know the destination address for a packet coming from internet? So to which this thing it has to go? So what you have to do, this NAT router has to do, it has to use some IP address, one IP address table. So in the simplest form, a translation table has two columns, the private address and the external address. So when the router translates the source address of the outgoing packet, it also makes note of destination address. So whenever NAT router is sending an information from a private IP address, it also notes the destination. When some information from the destination comes back, so it can translate it to, or it can give the information back to that private address which has requested it. So that is one of the idea. Then another idea is using pool of tables. We have a pool of tables like this. So using this we can calculate, or we can see how this thing forwarding is taken place or converting is taken place. The next part is forwarding of IP packets. This is not there in your syllabus, so I am finishing this video here. So up to this point, that is network address translation, and how network address translation is done by a NAT router, that is there for your syllabus, right? Up to 32, slide number 32 is there in your syllabus, right? So thank you for listening. If you have any doubts, please write it in the comment section. Okay, thank you. Have a good day.